In today's video, we will be deriving a new rule for taking derivatives. This new rule will be a generalization of some of the more familiar rules that you might already know. For example, the power rule, or the rule for when you take derivatives when there is a variable exponent and constant base. So we will be addressing how to take derivatives of a function like x raised to the power of x, or maybe how do you take the derivative of sine of x raised to the power of cosine of x. And in general, how do you take the derivative when you have a variable base and a variable exponent, right? How do you take the derivative of a function raised to another function, f of x raised to the power of g of x? So just to recall that if a is some fixed constant, then you probably remember the power rule. To take the derivative of x raised to the power of a, where x is a variable and a is a constant, then it's just the power rule, right? You bring the exponent down and you subtract 1 from the exponent. And to be a little bit more general, instead of just having x on the bottom, you can have any function of x, call it f of x raised to the power of a. And a similar rule applies. You bring the exponent down, you subtract 1 from the exponent, and then by the chain rule you have to multiply by the derivative of the inside, which is f prime of x. In a similar manner, you can take the derivative of an exponential where the base happens to be constant but the variable is in the exponent. And in this case, the rule is you leave a to the power of x as is, but then you have to multiply by the natural logarithm of the base. And in a similar manner, we can sort of generalize this, where instead of having just x in the exponent, we can have any function of x. So a raised to the power of f of x, and we just have to apply the chain rule. So the derivative of a raised to the power of f of x is just a raised to the power of f of x multiplied by the natural logarithm of the base, but then by the chain rule we have to multiply by the derivative of the exponent, which is f prime of x. Okay, so now we can actually begin deriving a rule, and I would like you to recall the following property of natural logarithms and exponentials. That is, when you take e raised to the power of the natural logarithm of y, then the e and natural logarithm cancel out and you just get y. So if you were to think of f of x raised to the power of g of x as y, then you would probably agree we can write this as e to the natural log of y, right? That y is f of x e to the power of g of x. These two things can cancel out, we'll get back here. And now we can use another property of logarithms that lets us bring the exponent down. So now we can write this as e raised to the power of g of x times the natural logarithm of f of x. Now the whole goal here is basically that I don't know how to take the derivative of f of x raised to the power of g of x, right? There's no rule that helps me with this. But if I can somehow get rid of this exponent, then I'll be able to apply some of the rules that I already know. And using this e raised to the natural log, it actually lets us do that, right? It lets us bring the power down from f of x, and now we can maybe apply some sort of product rule, and that's where we're going to go with this. So now if I want to differentiate f of x raised to the power of g of x, that's equivalent to differentiating e raised to the power of g of x times the natural logarithm of f of x. In order to differentiate this, we know how to take the derivative of e raised to the power of something. Well, it's going to be exactly e raised to the power of something times the derivative of that something by the chain rule. And now we can finish off the calculation by taking the derivative of this part by using the product rule. Also notice that e raised to the power of g of x times the natural log of f of x is just f of x raised to the power of g of x. All you have to do is just go backwards in this computation. So you bring the power of g back into the exponent, and then you can cancel e and natural log and you'll get back here. And then we apply the product rule here to get g prime, natural log of f of x, plus g of x times the derivative of natural log of f of x. And what is that? Well, the derivative of natural log is 1 over the inside, right? So you get 1 over f of x, and then by the chain rule you have to multiply by the derivative of the inside, which is just f prime. So that's how I got this. And this gives us the following rule, that the derivative of f of x raised to the power of g of x is given by this somewhat complicated looking expression. Another way to come up with the same formula is actually to use implicit differentiation. I find this method a little bit cleaner, but we're basically doing the same thing. So in this case, we let y equal f of x raised to the power of g of x, and then we take the natural logarithm of both sides of this equation. So we take the natural log of both sides of the equation, and then we bring the exponent g of x down. That's the whole point of applying the natural logarithm, is so we can bring this exponent down and then use some of the rules that we already are familiar with to attack this problem. And so now, using the properties of natural logarithm, we get g of x times natural log of f of x. So now what we can do is actually differentiate both sides, the extreme left hand side and the extreme right hand side of this equation with respect to x. So that's what I've written over here, and we're going to be using implicit differentiation. So the derivative of the left hand side, well, what's the derivative of natural log of y? Well, it's 1 over y times dy dx, right, y prime. And on the right hand side, it's the same computation. We use the product rule and we get this, and then we can just multiply both sides by y and we get this. But now remember, what is y? Y, we defined it to be f of x raised to the power of g of x, and so therefore we get the exact same result as before. Lastly, I want to use the rule that we came up with to solve some examples and also verify some rules that we are already familiar with. So just to recap, if y is equal to f of x raised to the power of g of x, then we have derived the following rule. So now if f of x and g of x both happen to be x, then y is just x raised to the power of x. And now we can differentiate y with respect to x, and it's given by this formula. So we will get just x raised to the power of x, and then what's g prime? Well, that's just 1. And then natural log of f of x, which is just natural log of x. And then over here, g of x is x, f of x is x, f prime happens to be 1, so the x's cancel and you just get 1 here, and there we go. This is the derivative of x raised to the power of x. It happens to be this rule. Now let's consider f of x to be x and g of x to be some constant. So then we're looking at the following function, x raised to the power of a. So this is some power function. So I want to verify the power rule. So the derivative with respect to x in this case, if we just zoom out a little bit and look at the formula, well, it's just going to be f of x raised to the power of g of x, which in this case is x to the a. G prime in this case, g of x is a constant, so the derivative is just 0. 0 times the natural log of f of x, which is just x, plus g of x is just a, and then f prime, which derivative of x is just 1, f of x is just x. And so this simplifies, right? This is just 0. We can bring the a out front. We have x to the a divided by x. That subtracts 1 from the exponent. And this verifies the power rule, right? This is something we're familiar with. Okay, so this brings us to the end of this video. So in this video, we were able to derive a pretty cool rule for taking the derivative of f of x raised to the power of g of x. This is a more powerful rule and a more general rule than usually what you learn in some of the first semester calculus courses. And this might be useful to keep in the back of your mind. If you found this video helpful, I would really appreciate it if you could leave a like, and you can always subscribe for more math videos. If you have any questions or comments, please feel free to leave them down in the comments below. I would be happy to respond.